this lecture, we're going to talk about an important concept in quantum computing, quantum reversibility. This lecture will be broken up into two parts. To begin, we'll start with a thought experiment. We're going to think about a quantum system as marbles in a box. So we have some red marbles, some blue marbles, and we're going to have a state of a marble be such that when it's pulled out of the box, we don't know if it's going to be red or blue until we look at it or measure it. So we can say that that marble is in superposition of being either red or blue. So until we observe these marbles, we measure them, we don't know if we're going to get a red marble or blue marble. So how easy is it for that system to change? We have a probability associated with the likelihood of seeing either a red or blue marble, and that is going to be determined by the number of red or blue marbles within that box. So that will fix the probability of observing one or the other. We don't know which one we're going to see until we actually select one from the box. So because this is a closed system, it's not going to be easy for it to change. So the state of our system is relatively stable. What happens, however, when a hole appears in the box? Well, we could lose some of the marbles, and that will cause the likelihood of observing one or the other to change. So the state of the system is no longer stable in this case because some of the marbles could fall out. It could accidentally be changed. So this brings us to an important concept in quantum computing, decoherence. Quantum state within our qubits is very fragile, and it's highly susceptible to accidental interactions with its environment or even accidental interactions with other qubits. So decoherence is the loss or modification of qubit state information that is accidental. So we can think about this in the terms of energy lost through heat dissipation. So some of that energy that we might have, maybe heat, is lost to the environment. So decoherence causes state change. That can cause a state of ket1 to become a state ket0, or it can cause a superimposed state to change its phase information from its original state, or it can cause it to collapse to either 0 or go to a value of 1. So that brings us to reversibility, a requirement for quantum operations. We don't want to lose any information before measurement. So we want to say, we don't want to lose any information about our quantum state. So prior to measurement, any quantum computation must be able to be reversed. So if we have a matrix U representing our quantum state, it is reversible. So we can have an input to our circuit recovered using the output and the function inverse, which we are going to call U raised to -1. So for example, if we have an initial quantum state of psi 0, that's transformed by a quantum state U, so that's just an arbitrary operation, and we get a resulting state, psi 1, we can recover our original input by taking psi 1 and multiplying it by the inverse operation. Let's look at a couple gates to see if they're reversible. We'll start with NOT and swap operations. So here we have a ket0 being transformed by a NOT operation to get a ket1, and then a ket1 0 operation being transformed by a swap operation to get a ket0 ket1. So if we take that output, send it back through the gate, we see that in both of these examples, we recover our original input. So we see that we end up getting our original input of ket0 and our original input of ket1 0. So we see that these functions are not only reversible, but they are their own inverse function. So let's check out C0. Is C0 reversible? So here we have all the input combinations for 2 qubits. So 1 0, 1 1, 0 0, 0 1. And we can see that we get our outputs that are determined by our transformation matrix. If our control has a ket1 value, we flip the value or not the value of the target. So we see that happening in these 2 cases. But we can see something interesting. So let's take the 1 1 output and send it back through the C0. Well, we get an output of 1 0, and that was the original input. So we can see that by running these gates twice, we're able to get our original input state. So we have these 4 unique input combinations and 4 unique output combinations. And that's another thing that we have associated with a reversible operation, a reversible 2-qubit operation. So let's check out the HGate. Is it reversible? If we have a ket 0 or a white ball going into the HGate, we get our superposition state that has no phase. And then if we pass that back through the HGate, we recover a white ball or a state ket 0. If we send a state ket 1 through the HGate, we get a superposition with phase. And when we send that back through the HGate, we get our original state of a black ball or a ket 1. So yes, the HGate is also reversible, and it's its own inverse function. Let's take a second to look at reversibility and superposition. So reversibility of quantum gates also applies to arbitrary superpositions. So if we have the NOT gate, for example, we can see that if we take the output from the first time that we transform state by the NOT gate, we can pass that back through the NOT gate and recover our original input state. You can work out the math to double check this. So we can see this in the following way if we have arbitrary superpositions. So we have A and B associated with the probability amplitudes of ket 0 and ket 1 respectively. We can see that the NOT gate effectively flips them. Well, if we take that original output and pass it through a second NOT gate, we can see that we recover our original input state. So the reversibility of quantum gates also applies to qubits and superpositions.